Hello, in this lecture we continue with our discussion on multiprocessor scheduling algorithms for real-time periodic independent task sets. Those are used in embedded systems. And we saw in the last example that algorithms which allow proportionate execution progress of tasks in the system succeed on multiprocessors in providing high resource utilization. We saw how greedy algorithms such as EDF, which allow the task with the earliest deadline at any scheduling point to execute, or LLF, which allow the task with the least laxity to execute at any scheduling point, fail on multiprocessors, but tasks which allow proportionate progress of execution. For example, in the last example we saw that every 10 time slots task 3 task 3 must execute 2 parts of its overall 8 units of execution requirement. In order to such a proportionate progress allowed it to complete its deadline by time 40, and thus we saw that algorithms allowing proportionate execution progress of tasks to succeed on multiprocessors. The first algorithm that was designed on this idea of proportionate execution progress was the PFair algorithm designed by Sanjay Barua way back in 1996, and it was the first multiprocessor scheduling algorithm for real time periodic tasks which allowed full resource utilization. We will now have a deeper look into this algorithm. So, this algorithm works by dividing each job of a task into unit length subtasks, where a subtask is that quantum of work that can be completed within a time slot of execution provided by the operating system. So, a time slot of execution is the least amount of time that can be shared that is given by the operating system. So, within a time slice only one task can execute. Across time slice at the boundary of time slice we can choose which task should be executed next. So, subtask is that amount of work that can be completed within the duration of one time slice, or sorry, one time slot. Okay. Now, this PFair algorithm progresses by scheduling the most urgent subtasks at each time slot to ensure fairness. So, PFair algorithms, how does it proceed? It finds out among all tasks at a given time which of the subtasks of the task has the most urgency. Okay. Based on that, it defines it finds out which subtask to schedule next at any given time slot boundary. So, therefore, what we are saying, we have jobs of tasks and the jobs of tasks are divided into subtasks. The subtasks are sequentially numbered from 1, 2, 3, 4 likewise, and we find out a few subtasks of each task at any given time. A few subtasks of each task has already been executed. Now, we have the next subtasks of each task to execute. Among those next subtasks, the PFair algorithm finds that subtask or that set of subtasks which are the most urgent and schedules them on the m available processors in the system. Okay. And PFair scheduling, or this proportionate fair scheduling proposed by Barua as it is called PFair, this PFair algorithm says that each task must must complete EI units of service every PI time units. In fact, it says that each task should progress based on the ratio EI by PI in proportion to the ratio EI by PI, which is also called its utilization UI. So, the execution should progress in proportion to this value EI by PI. Therefore, ideally the ideal rate at which the service should be provided to any task Ti is given by EI by PI into T. So, let us say that this EI equals to 5 and this PI equals to 10. and therefore ei by pi. So, therefore, in this case ui equals to 1 by 2. So, the ideal rate at which execution should progress is given by ei by pi into t. So, after 1 unit of time, the ideal progress says that the task Ti should complete half of its subtask. By time unit 2, it should complete one part of its subtask, one subtask. So, by time unit 3, it should complete 1.5 subtasks. By time unit 4, it should complete 2 subtasks. By time unit 5, it should complete 2.5 subtasks, and by time unit 6, it should complete 3 subtasks. Why? Because its utilization is half. So, the rate at which it should be provided service is at the rate of ei by pi into t. However, we said at the beginning that within each time slot only one task can execute. So, therefore, either I will give the processor for the entire duration of one time slot to a given task, or I will not allocate that processor to that task. So, a subtask will either fully execute, 1 unit of the subtask will execute, or the subtask will not execute at a given time slot. Therefore, this ideal execution rate provided by this PFair, this ideal execution rate cannot be followed practically in practice. So, PFair told that you cannot follow this execution rate ideally, but what can you do is you can approximate this ideal service rate as closely as possible. So, what it said is that you execute at least, you cannot execute these many subtasks at every time slot, fine, but you can ensure that you will at least execute ei by pi into t, floor of ei by pi into t subtasks, which is an integer, and or ceiling of ei by pi into t, which is also an integer. So, the amount of allocation, the amount of work for Ti that should be completed at time t should be upper bounded by this much, this value, and should be lower bounded by this much. Okay. So, what happened is that at the end of time 1, therefore, at the end of time 1, we can at most complete 1 unit of execution, or we can complete, we may not give this processor at this time slot to time I. In that case, it will only have received 0 units of execution. Why this is possible? Because at the end of 1, I can the floor of ei by pi into t is 0, because it is half. So, ei by pi into t is half at the end of 1. So, floor of ei by pi into t is 0. So, you are allowed to complete 0 units of execution to ensure p fairness, and you can at most complete 1 unit of execution, because ceiling of ei by pi into 1 is 1. So, you can complete at most 1, and you must complete at least 0. However, at time 2, what happens? At time 2, this floor is half into 2, which is 1. So, the lower bound is 1 here, and the upper bound is also 1. So, at the end of 2, you must exactly complete 2 units of execution. At the end of 3, what happens? By the end of 3, you see that the floor of ei by pi into t is given by 1.5. So, sorry, ei by pi into t. So, ei by pi is half into 3 is 1.5. So, floor of 1.5 is 1. So, you must complete 1 unit of execution, and you can at most complete 2 units of execution, because ceiling of 1.5 is 2. By the end of 4, you must complete 2 units of execution, and likewise. This is what is ensured for the PFair algorithm. So, what am I allowed to do? So, suppose the actual allocation which satisfies an actual schedule which satisfies PFair must guarantee this for all tasks in the system. And so, this blue line is a perfectly valid PFair schedule. So, this has said that it allocated the processor to Ti at time between 0 to 1 and completed 1 unit of execution at by 1. It did not allocate the processor between 1 to 2. So, the amount of work completed remained at 1 between 1 to 2, and then it did not allocate the processor between 2 and 3, and so at 3 the amount of work completed was 1. This is also perfectly valid because it satisfies the lower and upper bounds. Between 3 and 4 it again allocates the processor. So, by 4 it completes 2 units of execution, lower and upper bound is satisfied, absolutely valid. Likewise, it does not allocate the processor between 4 and 5. So, at 5 it has just completed 2 units of execution, it is still valid, lower and upper bound satisfied. Between 5 and 6 the processor is allocated to Ti. So, at 6 it completes 3 units of execution, then it again allocates the processor at 7 to this processor let us say, and it completes it completes 4 units of execution by 7, and this is also perfectly valid because both the lower and upper bounds are satisfied. So, between 5 and 6 and between 6 and 7 the processor is allocated 2 consecutive times to this task which has an utilization of half, and the lower and upper bounds are satisfied, and this blue line is a perfectly valid PFair schedule. However, let us say if the processor is again allocated to this task at this time slot 8, it will complete how many? It will complete 3, 4, 5 units of execution by 8, which is invalid, and this will make it an invalid PFair schedule. Okay. With this understanding, we proceed to ERFair scheduling, which is a derivative of the PFair scheduling. In fact, it is a work conserving version of the PFair scheduling, meaning that it does not allow a processor to idle if we have ready tasks to execute. Okay. So, in the previous in the previous algorithm, in the PFair algorithm, we saw that the processor can remain idle if this upper bound is reached. Let us say you have no other task in the system and you have completed 1 unit of execution by time 1. You cannot allocate the processor to Ti because it has already completed 1 unit of execution by time 1, and between 1 and 2 you cannot allocate the processor to Ti to meet this because this upper bound will be violated. Now, if there are no tasks to execute no other tasks to execute in the processor just remains idle between this time at this time. Okay. Now, if you have ready tasks, if the subtasks have arrived in the system and the tasks and the subtasks are all there in the system, while a task is ready to execute, not allowing the task to execute is not good, because the processor just remains idle doing nothing. ERFair removes this constraint. So, a work conserving global multiprocessor scheduling methodology for hard real time repetitive tasks, in fact for periodic tasks, task sets with fully dynamic priorities, meaning that the subtasks the priority of the relative priority of the subtasks of a task change over time. Okay, because the urgencies of the subtasks change. So, the jobs have not only the jobs have has dynamic changing priorities, but even the priorities within a job of a task can change. Each subtask can have a distinct relative priority with respect to other tasks, and hence it is an algorithm with fully dynamic priorities. So, ERFair scheduling is obtained from PFair by removing the upper bound on the amount of work that should be completed by time t. Okay. So, this part still remains, but this upper bound is removed. So, it is just said that it must complete this amount of execution. So, it must complete 2 amounts of it must complete at least 0 units of execution by time 1. It must complete at least 2 units of execution by time 2. It must complete at least 2 units of execution by time 3. It must complete at least 3 units of it must complete at least 1 unit 0 unit of execution by time 1. It must complete at least 1 unit of execution by time 2. It must complete at least 1 unit of execution by time 3. It must complete 2 units of execution by time 4, and likewise. However, the upper bound can be anything. It can complete, say, the processor can be continuously allocated to task I for these 4 consecutive time slots, say, and the task is perfectly eligible to complete 4 units of work by time 4 if the processor has no other task to do other than allocating itself to this task. Okay. So, ERFair allows this, PFair does not. Now, how does PFair guarantee this? How does PFair find out the urgency? We said that how PFair finds out the urgency among all other tasks is something that we have not looked at. We found out what PFair guarantees, but how does it guarantee we have not seen. So, this is what we will see now. So, given the task weights, PFair finds pseudo deadline dji of the jth subtask for task I. I said that the subtasks of a task are numbered. So, if these are the subtasks of a task 1, 2, 3, 4, 5, 6, and let us say these 6 subtasks comprise the job of the first one job of this task, and these jobs repeat. Okay. So, this one is subtask 1, this one is subtask 2, this one is subtask 3 of task I. So, the jth subtask of task I, the deadline for the jth subtask of task I is denoted dji. So, dji is the jth subtask of task I. Now, this pseudo deadline says that you must do this. You must complete the first job, the first subtask by what time? Pi by ei. With respect to the previous algorithm, we had pi equal, with respect to the previous example, we saw that for that task ti we had pi equals to 10, pi was 10 and ei was 5. So, pi by ei equals to 2 by 1. Okay. Okay. So, it says that the first job should complete by 2. So, j is the subtask number. So, d of 1 I equals to 2. Why? Because 1 into 2 into 10 by 5, or 1 into 2 by 1, which is 2. Now, the second job must complete by 2 into 2 by 1, which is 4. So, d 2 I equals to 4. Likewise. So, if we say, if we have another task, let us say we have ei equals to, let us say 2, and we have pi equals to, let us say 5. So, it is 2 by 5. So, the first job should complete. So, for this task d 1 I equals to what? 1 into 5 by 2. So, 5 by 2, 1 into 5 by 2 ceiling, which is equals to 3. Okay. So, the first job should complete by 3. The second job should complete by what? 10 by 2, which is 5. So, d 2 I equals to 10, 5 into 2 by 2, which is 10. The third job should complete by 3 into 5, 15 by 2. So, the third job should complete by 3 into 5, 15 by 2, which is 8. So, likewise it progresses. This is what ERFairness wants. Now, how does the scheduling actually progress? The algorithm is as follows. So, this is what we just studied. For each subtask of each task, we provide a pseudo deadline like this. Now, some of the subtasks at any given time, a few subtasks, let us say, of each task has already been scheduled, and we have to determine which is the next subtask to execute. So, how does it do this? So, schedule subtasks with the earliest pseudo deadline first. This is the overall idea. How does it do? It arranges subtasks in a mean heap, and in this mean heap, the key is the pseudo deadline of the next subtask of this task. So, it arranges the tasks in the mean heap, and how does it arrange? The key value for this mean heap is the pseudo deadline for the next subtask of each subtask of the next subtask of each task. So, therefore, at the root of the mean heap we have that task whose pseudo deadline is least or earliest. So, extract the task at the root and execute, because it is the most urgent. Now, if you have m processors, you extract the m most urgent subtasks, or you sequentially extract m tasks from the root with the least pseudo deadline, and then you execute it. After execution, you recalculate the pseudo deadline of the next subtask and insert that back into the heap. Okay. So, this is how execution is going to progress. Ties between multiple subtasks having the same pseudo deadline is broken using a set of tie breaking rules. So, you can have multiple say subtasks of tasks whose utilizations are different, but multiple subtasks can have the same next pseudo deadline for its next subtask. So, the pseudo deadline is same for multiple say subtasks. Then what do? You have a set of tie breaking rules, which we will not discuss as part of this course. There are actually two tie breaking rules. One is called the successor bit, the other is called group deadlines, which we will not go into in this course. For this course, we say that if such a clash happens of multiple subtasks having the same pseudo deadline, we break it arbitrarily. Now, what is the complexity of this algorithm? The complexity of this algorithm is big O of n, big O of log n per time slot per processor. So, why do we have this? Suppose, why do we have this? We have to build a heap, which is a one time procedure, big O of n, which we neglect at the beginning, and then what happens? We take out the least, we extract the task with the least pseudo deadline, which is O1, fine, but then we have to reheapify and rearrange the heap, which is a log n operation, big O of log n operation. And for m subtasks, if we have an m processor system, then the total overhead for extracting the m subtasks at each time slot and reheapifying them is of the order of big O of m LG, big O of m LG n. Okay. So, this is the complexity for this algorithm. So, what are the strengths of this ERFair algorithm? The first is that it is optimal. It allows full resource utilization. The scheduling bound being summation ei by pi must be less than equals to m the number of processors. We saw for EDF that summation ei by pi or ui has to be less than 1. Therefore, EDF we said was an optimal algorithm which allowed full resource utilization in uniprocessor systems, and in this case for the ERFair algorithm, in fact for the PFair algorithm as well, it says that if you have a task set whose total utilization is less than m, you will be able to feasibly schedule that on this multiprocessor system. Okay. So, this is what it says. So, therefore, summation over ui less than equal to m is sufficient, is the sufficient condition for schedulability on multiprocessor systems using ERFair. It allows guaranteed quality of service in terms of saying that it allows you to reserve x units of time, or rather ei units of time for task A out of every y time units. So, we said that such kind of execution progress guarantees or quality of service guarantees can be provided when we use this, and this property can be useful in many embedded systems which execute a lot of tasks together, let us say streaming tasks along with other best effort downloads together. So, if a set of tasks have such a quality of service requirement like that for streaming tasks which must execute at a certain rate, PFair algorithm is a good alternative. Although and its derivative ERFair is a good alternative. However, there are other constraints which we will look why that which is why ERFair is not always practically used. Another good property of ERFair is that it allows temporal isolation of as we will see, it provides temporal isolation to each task, each client task from the ill effects of other misbehaving tasks attempting to execute for more than their prescribed processor shares. So, we have said that each task is guaranteed a processor share. It reserves x units of time for task A out of every y time units, because it always finds the earliest pseudo deadline among all subtasks and executes it first. So, if a task takes more execution time than it is stipulated to take, it is that task which only suffers. Other tasks whose execution urgency becomes higher will get the processor, and it is only this task which will be delayed in its completion. So, this is somewhat this is a very good temporal isolation that is provided, and it is often important in embedded systems, safety critical embedded systems running critical tasks, and this property to some extent we saw was also provided by the rate monotonic algorithm. How the execution progress of a task can only be affected by its higher priority task, it cannot be affected by lower priority task. Here we are saying it is a much stronger condition which says that it will never, it does not matter high priority, low priority, because the priorities are dynamic and we have priorities associated with each subtask. We can say that a task will never be affected by other misbehaving tasks which take more time to complete than it was stipulated to take. Suppose a task was allocated EI amount of time to complete, but it takes more than that to complete. That misbehavior will not affect other tasks. This is what ERFair guarantees, and this makes it applicable to a large range of domains, CPU, networks, embedded systems, etc. It allows graceful degradation in times of overload, meaning that suppose this condition is not met. So, what happens is that this summation becomes greater than m, then everybody is affected by the same degree. Why? If you see the way ERFair algorithm is implemented at each time slot, it finds out the task with the highest urgency. This relative urgency is going to remain same even if summation EI by PI becomes higher than m. So, everybody will be affected by the same degree, everybody will get delayed by the same amount and by the same proportionate degree. And this is why ERFair provides graceful degradation for all tasks in times of overload, and it allows efficient handling of dynamic task arrivals and departure. So, at any point in time handling dynamic arrivals, so a new task arrives and an existing task departs, this handling is very simple for the ERFair algorithm. We just need to check if after the arrival of the new task, is this condition still satisfied. So, if I accept the new task, will summation EI by PI still remain less than m? If this is satisfied, the new task can be allowed into the system. If an existing task departs, it just departs, does not matter, because ERFair the upper bound on execution, there is no bound. So, it will just happen that other tasks will execute at a higher rate in a proportionate manner, and it will consume the CPU. It will take the CPU that is left idle by to some amount by the task that has departed. That space, that additional space will be proportionately shared by other tasks, and this will naturally happen. We do not need to do anything special for that, and hence task arrival and departures are easily handled in ERFair systems. However, ERFair schedulers also have some significant weaknesses. So, the first is high scheduling complexity. It uses a mean heap to determine the most urgent operation deadlines of subtasks at each time slot. This is what we saw, and this incurs big O of m LGN at each time slot, and this is significantly high if the number of processors and especially the number of tasks in the system becomes very high. Okay. And this is one big problem, and the second big problem is unrestricted migrations and preemptions. It is a direct consequence of fully global scheduling, and we are saying that at the end of each time slot we decide which subtask is the best to schedule, and we schedule in that order. And therefore, there will be a lot of preemptions and there will be a lot of interprocessor task migrations. And due to this, there will be ignorance of affinities of tasks towards the processor where it last executed, and of processor caches towards the task it executed recently. So, there could be a large number of cache misses, and such cache misses could be costly. Even in let us say in closely coupled systems where you do not have shared cache at a close enough level, such cache misses could be costly, because the transfer rate, you have to transfer the code and data of a task from one processor to the other, from the local cache of one processor to the local cache of another processor, and this could be quite significant. And if it is a completely distributed system, such migrations could be very huge, the overheads could be very huge, and this algorithm can become unusable. So, ERFair is a good algorithm for say closely coupled synchronous multi-core systems, let us say with moderate number of tasks, not very high. So, for systems in which these overheads can be controlled, ERFair is a good algorithm to use. So, with this we highlight this migration problem of ERFair. Let us say we have two tasks, one is 8 by 4, the other is 10, one has an utilization 4 by 8, which is half again, and the other has an utilization 5 by 10, which is half again. So, you have two tasks, T1 this one and T2 this one. Okay. These are the two tasks we have here, and therefore, both have a utilization of half. So, if you see that both have the first subtask of both will have a pseudo deadline of 2, and hence one is going to execute. Okay. So, they will take alternate turns to execute, each of them will take alternate turns to execute, because after let us say subtask 1 has executed for task 1, the second subtask has a pseudo deadline of 4. The first subtask of task 2 has still not executed, so its pseudo deadline is 2. So, therefore, this becomes more urgent than the second. So, for task 2, the first subtask of task 2 becomes more urgent than the second subtask of task 1 at this position, at this time instant 1, at the boundary of 1, after task 1, the first subtask of task 1 has already executed. Then at this time point 1, the first subtask of task 2 becomes more urgent, its pseudo deadline is lower than the second subtask of task 1. So, the first subtask of task 2 executes here, then again this alternative arrangement proceeds one by one, but the deadlines by which actually we need to finish tasks is 8 and 10 for these two jobs, for the first jobs of task 1 and task 2, right. So, the deadlines are much later, but we are doing that, but we can do better than that. As we saw that if you had done deadline partitioning, what you could have said is that within time 8, which is the first deadline starting from 0. So, if you look from 0, the first deadline is at 8, the second deadline is at 10. The first deadline is for task 1, the second deadline is for task 2. And we can say that by 8, it is sufficient to complete 4 units of work. So, 4 by 8 into 8, which is 4 units of work for task 1 and also 4 units of work for task 2. Okay. So, this is 4, this is 5. So, it is sufficient to complete 4 units of work for task 2 and 4 units of work for task 1. So, this is what has happened, and you need not have incur preemptions and migrations in between. You can consecutively execute 4 subtasks, and you can safely do that, because we know that the first deadline that is going to come is at 8, and the proportionate progress at deadline boundaries is sufficient to meet all deadlines, as we saw in the example previously. So, it completes 4 units of execution, and then task 2 completes 4 units of execution, and then between 8 and 10 I have a slice size of 2, and within this 2 I know that if I have 4 and 8, and within this 2 I therefore must complete 1 unit of execution for task 1, and again 5 by 10 into 2, which is 5. So, 1 unit of execution for task 2. So, I must complete 1 unit of execution for task 1 and 1 unit of execution for task 2 between 8 and 10. If I can ensure this, I can ensure that at all deadline boundaries at which I actually check whether I meet or miss deadlines, I will be able to guarantee all deadlines, because all tasks progress fairly by their ERFair degree. I can say that the tasks had ERFair at 8, the tasks are ERFair at 10, all tasks. So, if they are ERFair, they will also always meet deadlines. So, we are saying that because we are checking deadlines only at actual deadline boundaries, it is sufficient to violate the exact ERFair requirement within consecutive deadlines. This is what has happened here. We have violated individual subtask pseudo deadlines, but we can still ensure the progress, that the sufficient progress has been made at actual deadline points. Okay. So, by this we can save migrations and preemption, but ensure full resource utilization, and this is the essence of the DPFair algorithm, which we will discuss next. So, DPFair has come within around the 2010. So, around 2010 it was first published, I suppose, in Real Time System Symposium, and then subsequent journal version of this work has come in 2011. So, it also basically is based on the fluid schedule. So, this is the fluid scheduling rate which we just saw, and we said that this one is a CPU rate of 1. So, this angle is 45 degrees, meaning that if you allocate, so this position, this duration is essentially E, this workload E. So, what happens is that if you allocate the processor continuously, from release, it will complete at time E. If it has an execution requirement of E, and you allocate the processor continuously only to this task, then it will complete the work at E, and therefore, this one will have a slope of 45 degrees. So, slope of 1, sorry, this angle is 45 degree, and this is a slope of 1. So, it will exactly complete its work at time E, and this part it will remain idle here. Now, how long can it wait? It can wait, it is saying this is the 0 laxity curve, this is again 1, which means that this one, this is again E. So, this is the point of 0 laxity. That means you have E amounts of work remaining. You did not allocate the processor by this whole amount, by this whole time, and then at this amount you have exactly E amount of work remaining to be completed within this within this time of E. Within this time E, you must complete E amounts of work, and then after this time, from this time, to complete your work by the deadline, you must continuously allocate the processor and complete your work here. Okay, this is what it says. Now in between the actual schedule can proceed. So EDF, any algorithm, if you look at, it will progress something. If the schedule is valid and does not violate deadline, then what will happen, the actual execution can proceed in any curve like this. However, it has to execute something in between. It can be anything else as well. It can be anything else as well, but it has to complete, it has to remain within this region, this red region, it has to remain. If it violates this region, it cannot go on this side, because this means that you are executing at a rate more than 1, which is not possible, because we know that at most this much amount of work can be done if the whole processor is allocated to the task for this entire time. So it cannot progress on this side. It cannot progress on this side because deadline will be missed. So it must complete at least this much of execution at this time. It must complete at least this much of execution by this time from the beginning. It must complete at least this much of execution from this time. It must complete at least this much of execution by its deadline to ensure that deadline will be met. Suppose it does not, it is somewhere here and it does not complete this much amount of execution at this point from the beginning. It means that even if you allocate the full processor to this, it cannot complete its full execution. It will only complete about this much amount. So this much amount of execution will still be left to be completed, and hence it will miss deadline. Okay. So this is what this figure says. Now our deadline fairness, essentially deadline partitioning fairness, said that you should complete your fair amount of execution progress by deadlines. Okay. We said that for that example in which we had these two tasks of 4 by 8, U 4 by 8, U1 4 by 8 and U2 5 by 10. For these two tasks, we found that by 8 we should complete 4 units of execution both for task 1 and task 2. Why? Because 4 units of execution was the fair execution progress at deadline boundaries. So this one says that this is the amount of work that you must do by this deadline for a given task, and within this, what DP fairness says that within this it does not check fair execution progress. So you need not absolutely follow this ideal execution rate. You need not exactly follow this ideal execution rate within this time. You are allowed to be within this at some point in time. At any point in time you are allowed to be anywhere within this, but the end of this time, what DP fairness wants is by the end of this time you must complete this much amount of work. And again in the next deadline, by the next deadline you should complete this much amount of this much amount of work. And this is what it says. So if the system has various deadlines, as we saw 8, 10, and then we will again have a deadline at 16, 20. Likewise, if we go on having, the system has numerous deadlines, the DP fairness prescribes that for each task you should have completed your fair amount of execution at each deadline boundary, and that should be guaranteed for each task. So this is the amount of work that should be completed for task 1, for the first job of task 1, and then for the second job of task 1 again it should progress in a deadline partitioning fair manner, DP fair manner at each deadline boundary. This is what it says. Okay. So what are the rules for DP fair scheduling? You partition time into slices based on system deadlines. So what are these system deadlines? These are the period boundaries of all subtasks. So you have multiple job boundaries, or rather the job boundaries, the job deadline or period, task period boundaries of all tasks over time. And then at any point in time it finds the next earliest deadline boundary, it allocates shares. For example, we said that in the first time slice 0 to 8, it must complete 4 by 8 into 8, which is 4. So, this 4 is the share, execution share of that task T1 for in the time slice of 8, duration 8. Okay. So allocate each job a per slice over workload equal to its utilization times the length of the slice. So, this was its utilization, this was the length of the slice, and therefore, it allocates each job of each task a per slice workload equal to its utilization times the length of the slice, and then schedule jobs within each slice in a way that obeys the following rules. So, we just saw the rules and we just chalk them down again. Always run a job with 0 laxity. So, you cannot delay a job with 0 laxity. Within that, you can be anywhere. You need not for example, abide by the exact ERFair say execution progress guideline. You can violate, and you never run a job with no workload remaining in the slice. Okay. So then you are saying that if you do not execute more than your workload. So, it means that this version of the PFair algorithm can allow a bit of non-work conservation, meaning that if your amount of work has completed in a particular time slice and you do not have any other task to execute, you still do not execute more than what you are prescribed to execute in the total time slice. So, more than 4 time units of execution you do not execute within this time 8. So, this is where this is what PFair suggests, so that no deadlines will be missed, but we can have mechanisms to bypass this as well. Okay. And do not voluntarily allow more idle time than m minus ui into length of the slice. So, for any task the ui is its utilization. Now, what does this particular expression tell me? If you see m into length of the slice, m into length of the slice is the total number of time units available within the time slice, m number of processors, and on each processor you can execute for the length of the time slice. So let us say 8 is the length of the time slice and you have 4 processors, then 8 4s are 32 total time units of execution is possible in this time slice. Okay, of 8 time units. And what is ui? Ui is the amount of work that is needed for a given task. Okay. So, ui is the amount of work that is needed to be completed by a given task. Within, let us say, this 8 time units, I need to complete 4. So, ui into length of the time slice is 4 for say task 1 here for this case. Okay. So, this one says that you cannot voluntarily allow more idle processor time than this, because if you allow more than that, then you cannot complete the set of jobs that the set of total workload that you have within the time slice. Now, we provide a strategy for execution within each time slice. How does execution within each time slice progress? And that happens using the dpwrap algorithm. Now, all time slices are equivalent up to line scaling. So, normalize time slice by 1. What does this say? It says that for all time slices, you normalize any time slice into a time slice of length 1. Okay. And then you do stacking and slicing as follows. We see the procedure here. Suppose you have a set of 3 processors and you have 7 tasks, and these 7 tasks have utilization 0.3, 0.5, 0.5, 0.6, 0.5, 0.4, 0.2. So, these are the 7 tasks, and we just stack the 7 tasks one after another onto this line, and we divide this whole set. So, these tasks are stacked one after another onto this line, and we divide this line into at the junction, at the integer points 1, 2, 3. Okay. We said that what is the idea? The idea is that we said that the processors are each of unit capacity. So, this is the total workload that can be handled by one processor. Okay. So, this can be allocated to say processor 1, this can be allocated to processor 2, this can be allocated to processor 3, and we can execute them. Okay. So, therefore, what we are doing? We are allocating this amount. So, 0.3 plus 0.5. So, this 0.3 plus 0.5 0.8. So, we allocate 0.2 here and we allocate 0.3 here. We allocate 0.3 plus 0.6 is 0.9. So, I allocate 0.1 here and 0.4 of this total 0.5 here, and we complete by 3. So, if you see this total workload, if you sum up the utilization, sum ui equals to 3 in this case. So, it is schedulable through because this algorithm DPFair is optimal. Okay. So, then we slice. We had stacked, we divided into processors and we sliced. So, this is the workload for processor 1, this is the workload for processor 2, and this is the workload for processor 3. And then for this is for any, we said that this is for a unit length time slice. Now, if your time slice is 8, you just multiply the amount of work that must be done for task 1. So, 0.3 into 8 is the amount of work for task 1, 0.5 into 8 is the amount for work for task 2, 0.2 into 8 is the amount of work for task 3 on processor 1, 0.3 into 8 is the amount of work for task 3 on processor 2, 0.6 into 8 is the amount of work for task 4 on processor 2. Likewise, it proceeds. So, these tasks which partially execute on one processor and partially on another processor must incur a migration, and these tasks cannot overlap over time, because this is a single piece of code, and it means that the first part of the work will be done on processor 2 and it will complete by this amount of time, and at this time within the time slice then task 3 will be migrated from processor 2 to processor 1 and start execution at this time after it completes on processor 2, and we can guarantee that it will never overlap if the total work, we can have an allocation like this, through this slicing, through this stacking and slicing, and if the processors are homogeneous, we can guarantee that if the individual utilization of the task is less than 1, then we can have an allocation where a task will never overlap on two processors. So, we can have like the task will complete on processor 2 and then it will be migrated to processor 1 and complete execution. Similarly, task 5 will first execute on processor 3 and then after it completes on processor 2, it will be migrated to processor 2. It will execute on processor 3 and then after it completes on processor 3, it will be migrated to processor 2, where it will complete its remaining execution by the end of its time slice. Okay. This is how DP wrap algorithm within DPFair progresses. So, we discussed two important algorithms, the three important algorithms rather, the PFair algorithm, the ERFair algorithm and the DPFair algorithm, which uses DP wrap within it to conduct scheduling. We said that PFair is the first optimal multiprocessor scheduling algorithm, but PFair and ERFair are the first optimal multiprocessor scheduling algorithms, but they put severe constraints on the rate of execution of the tasks, which is not necessary just to meet deadlines, and in doing that the algorithms become costly in terms of scheduling overheads, and also in terms of migration and preemption overheads, DP-wrap is a more recent algorithm which allows much better which fares much better in terms of its scheduling as well as migration and preemption overheads. In fact, DPFair can guarantee that within every time slice there will be at most m minus 1 task migrations, where m is the number of processors. So, DPFair can guarantee that the number of migrations within each task within each time slice will be at most m minus 1. For example, if we see in this case, we see that we have 3 processors and the number of migrations are 2, one from processor 2 to processor 1 for task 3 and the other from processor 3 to processor 2 for task 1. It also guarantees that the number of preemptions are also limited. So, number of preemptions is upper bounded by n minus 1, so where n is the number of tasks. So, within each time slice. So, DPFair guarantees that the number of preemptions will be at most n minus 1 and the number of migrations will be at most m minus 1 within every time slice, and hence its overheads are much lower than PFair and ERFair. With this, we come to the end of this lecture.